Everyone, I am Prof.Rajani Hardas going to discuss about static VAR compensator under the subject HVDC and PAC. Contents of presentation are as follows: features of HVDC, when to use HVDC, what are HVDC configurations, what is its working principle, its VAR characteristics, and how voltage control of HVDC is achieved, and lastly, its advantages and disadvantages. Features of HVDC are as follows. HVDC is the first family member of the PAC device family. It regulates the grid voltage, power factor, harmonics, and thus provides stability to the power system. It is a set of electrical devices for providing fast-acting reactive power on high voltage electricity transmission network. That means parts. It is an automatic impedance matching device designed to bring the system closer to negative power factor. HVDCs are used in two main situations. When HVDCs are connected to the power system for regulating transmission voltage, then it is called as transmission HVDC, and when they are connected near large industrial loads for improving power quality, then it is called as industrial HVDC. Please have a look on HVDC configuration. What are the parts of the system? The HVDCs are connected to grid through this step-down transformer. The HVDC, the conventional static VAR compensator used are mechanically switched reactors or mechanically switched capacitors. So, whenever a grid or system needs leading reactive power compensation, then mechanically switched capacitors are connected to the grid, and a vice versa case where whenever there is a requirement of lagging power compensation, then mechanically switched reactors are connected to the system. These were the traditional compensation methods used in past. After invention of thyristor and its use to the power system, that is its ability to handle high power system network, then this compensation used is based on thyristor. So the next two HVDCs came into picture are as follows. Those are thyristor connected reactor, that is TCT, or thyristor switch capacitor, TSC. Now, the thyristors are electronically controlled. The controller circuit is used for controlling firing angle of thyristors, which in turn controls the leading or lagging reactive power compensation. While doing so, the thyristors generate heat, and therefore cooling is required, and it is done through deionized water. While leading or lagging reactive compensation, we are doing the chopping of reactive load into the circuit. In this manner, undesirable odd order harmonics are injected into the system, and therefore the high power filter banks are usually provided to smooth the waveform. The voltage regulation is provided by means of closed loop controller. Sometimes remote supervisory control and manual adjustment of the voltage set points are also common. The working principle of SVC is as follows. If the power system's reactive load is capacitive, that is lagging, the SVC will use thyristor control reactors to consume VAR from the system and thus lowering the system voltage. Under inductive, that is lagging conditions, the capacitor banks are automatically switched in and thus providing a higher system voltage. In industrial applications, SVCs are typically placed near high and rapidly varying loads such as arc furnaces where they can smooth thicker voltage. Its VI characteristic of SVC, which shows the relationship between voltage and current of SVC. It is a dynamic VI characteristic, whereas system characteristic, where it crosses the dynamic characteristic, this point is called as quiescent point. The voltage control by SVC can be understood by taking the reference of VI characteristic. The power system is modeled as an equivalent voltage source Vs behind equivalent system impedance Xs as viewed from the SVC terminal. The system impedance Xs corresponds to short circuit MVA at the SVC bus and it is obtained as Xs is equal to Vb upon Sc into MVA, where Sc is the three-phase short circuit MVA at the SVC bus, Vb is the baseline voltage, line to line voltage, MVAB will be the base MVA. Thus, the SVC bus voltage is given by Vs is equal to SVC voltage plus ISVC into Xs. The SVC current thus results in a voltage drop of I into Xs in phase with the system voltage Vs. After knowing VI characteristic of SVC, following points are observed. The SVC bus voltage decreases with inductive SVC current and increases with the capacitive current. The intersection of the SVC dynamic characteristic and the system load line provides the quiescent operating point of the SVC. The voltage control action in the linear range is described as SVC voltage is equal to V reference plus Ix dot, that is SVC current ISVC into Xs, where ISVC is the positive if inductive and ISVC is negative if it is capacitive. Now we will see advantages of the slow in the SVC dynamic characteristics. What are its advantages? Basically, it reduces the reactive power rating of the SVC for achieving nearly the same control objectives. It prevents the SVC from reaching its reactive power limits too frequently, and it also facilitates the sharing of reactive power among multiple compensators operating in parallel. Now, after knowing features, VI characteristics, working principle of SVC, now we have come to a point which is advantages and disadvantages of SVC. SVCs are simple compared to mechanically switched compensation schemes because of its instantaneous response to changes in the system voltage is better. SVCs are cheaper, higher capacity, faster and more reliable than conventional dynamic compensation schemes such as synchronous condensers. However, SVCs are more expensive than mechanically switched capacitors.